Welcome everybody to our video for parallel programming. In this video we're going to talk about quantum computing. All of us know what classical computers are. We use them in our everyday lives. And recently you might have heard of some major companies like NASA and Google have bought a quantum computer. In this video we're going to talk about what quantum computing is, some applications of quantum computing, and then the future of computing in general. So let's get started. So first off, what exactly is quantum computing? What physicists noticed is that quantum particles exhibit interesting properties. And so one particular property is that quantum particles have a spin to them. So these particles can be spinning in multiple directions, but until we measure which direction it's spinning in, we can't tell exactly what it is. So we say that the particle has a superposition of spin directions. And so what this means is that before we measure which direction the particle is spinning in, it behaves as if it's spinning in both the directions at the same time. And so the question is, how can we apply this property to computation? Algorithms for quantum computers can be quite complex, and so we've decided to go through an example of one quantum algorithm called Grover's algorithm. And so I have here an example array, and so what Grover's algorithm does is it allows you to search through an unsorted array for some value, and it will give you the index of the value. And so the way Grover's algorithm works is we first start with all of our qubits, and we initialize them to be the superposition of 0 and 1. And so if we were to look at all of our qubits and we were to interpret it as a number, it has an equal probability of being any one of the indexes of our array. So we have 8 items in our array, and so that means that if we were to interpret the value of our qubits, it should be a number between 0 and 7. And so to represent the 8 different possible indexes, we need at least 3 qubits. And so if we were to initialize our 3 qubits to be the superposition of 0 and 1 with equal weights, we would have a graph that looks as follows. There's 8 different possibilities. The probability of finding our qubits in any particular state is 1 out of 8. And so the way that Grover's algorithm works is that it takes advantage of what's called an oracle function. And so the way that the oracle function works is that we supply it a function that will return true if the index is the location that we're looking for, and it returns false if it is not the location that we're looking for. After we apply the oracle function to our qubits, we'll get a graph that looks as follows, where all the probabilities are unchanged except for the index that we're looking for, and it will have a negative probability. And so when I say probability, so it's not truly a probability, but what we can do is we can interpret the size of the bar to be the probability of finding the qubits in that particular state. And so after we apply the oracle function, we can then apply what's called an operator. And so what the diffusion operator does, it's the same thing as inverting about the mean. And so as we see here on this graph, we've plotted the mean, and if we were to invert all the values about the mean, all of the indexes that are not the ones we're looking for, they are above the mean. So if we invert it, they will become below the mean. Their probabilities will decrease. Whereas the index we're looking for is a negative number, and if we invert that about the mean, then we'll get a number that is above the mean. And so after we apply the diffusion operation, we will get a graph that looks something as follows. We have to run Grover's algorithm multiple times for there to be a good chance of finding the qubits to be the actual index that we're looking for.
Okay, so now that we know how quantum computers work, we'll sort of know how quantum computers work, and now that we have the brief overview, I'm going to go into a couple different applications for quantum computers, specifically the applications that the only commercial company that manufactures quantum computers right now, likes to sell their computers for, and that's optimization. So quantum computers, because of the superposition states that they have, are basically tailor-made for optimization problems that are too large for conventional systems. And so what you do, so say for example our problem is cancer drug treatment, and we have 30 cancer drugs, and we want to find the optimal way to dose a cancer patient with these 30 cancer drugs. So what we do is we initialize all the qubits to have some value corresponding to those cancer drugs, and then we nudge them. This is directly from the D-Link website. We nudge them with with a magnetic field, and so that they move around, and they eventually will find the lowest energy state, because everything wants to go to its lowest energy state. And so once they find this state, that state will be the optimal way for those items that the qubits are modeling to be laid out. And so once we have this model, we need to simulate it so that we can see, given this model, what's actually going to be the output on the cancer patient from me giving them this dosage of 30 different drugs. And so what they do is we pair these $15 million quantum computers with conventional HPC systems, and we feed the model generated by the quantum computer into the traditional system, and then use that to model it, because quantum computers are not, and currently cannot actually simulate other things. They're mainly extremely good for doing, like I said, the models and optimization problems like this. There are actually several startups that D-Wave is a part owner of that use their computer for stuff like this. So D-Wave has a program, because their computers cost $15 to $25 million each. The only people that currently own them are the University of Southern California. NASA and Google have one that's at a NASA research facility that they use for machine learning models, and Lockheed Martin has one that they use to help optimize and do work on and model out the flight systems to control fighter planes. All of which, as you can see, are using that optimization level that the quantum systems are very good at. And so all of these systems are, again, paired with traditional HPC systems for the simulation part after the model has been developed. So if I have a health startup company and I want to design a new cancer drug, and I have a way to do that using a quantum computer, what D-Wave will do is I will sell them, say, 5 or 7% of my company in order to have time to run on their quantum systems, because of the large cost and large deployment infrastructure that's needed to support these systems, because the chip for the systems is approximately that big, but the whole system to support it would fill a medium-sized room, because they need all of the additional cryogenic support stuff to drop the temperature down. And actually the temperature in their systems is 180 times colder than deep space, and is actually the coldest known sustained temperature in the universe currently that we know of course. Okay, so another application of quantum systems is, in this example I'm going to use my mom for this. Using your mother for technical explanation demos is a fantastic tactic that everyone should really use. And so in this example, someone like my mom, if I said, "Hey mom, what do you know about quantum systems?" she would say, "Oh, that's what people are going to use to steal my banking information from my website." And I would say, "No, but that does bring up an interesting application for quantum systems." Most modern web cryptography relies on the fact that factoring very large integers into prime factors is extremely difficult, and can sometimes, for very large numbers, take longer than the age of the universe, which is completely impractical for obvious reasons. There actually is, so there's a quantum algorithm that can do this extremely quickly, and has been proven to do this extremely quickly, and has actually been used to break these forms of cryptography running on quantum systems, to allay the fear of someone who would say, "Oh, someone is going to take a quantum computer and they're going to use it and they're going to steal all my information and steal all my cat videos," which they're probably not going to do, because you already give them to like the NSA. The counter to this is, in the future, everybody may be able to have quantum systems in their houses, or you can rent them, but the infrastructure that's needed to support them is a lot, so that won't happen anywhere in the near future. And so the only people that can really support and use these systems are people like Google, NASA, the NSA probably is using them to steal your cat videos, and then like research universities and things like that, just because of the large cost. So that does sort of allay the average person that would know about quantum. They would think, "Oh, it's going to steal my data." But that's not strictly true, because the government's already stealing it in other ways, and the only people that can pay for these are people with large amounts of money, so it's not that much of a problem. There are actually several startups that D-Link is a part, or not D-Link. Totally wrong company. The coldest known sustained temperature in the universe currently. Their promo video was talking about that, and I was like, why don't they just sell like refrigerators?
You don't need something that cold.